All right, hello everyone. So the goal of my talk today is to give you a little taste of the optimization potential of disposal canisters and also show you some concrete examples of the first steps we're taking in that respect within the URAD work package Concord. So everybody understands what the disposal canister is, right? It's a box in which you put the waste, and while it is intact, nothing bad happens. The public definitely understand this more easily than swelling, self-sealing, self-healing, diffusion-limited clay, right? And then the issue is that immediately once you explain this, the first question both the public and the expert asks is how long? So the canister lifetime gets a lot of focus and a lot of questions from everyone. And as a canister designer, you know that the bigger the number in your answer is, the more people are happy. So the immediate questions that come afterwards is how can I make the canisters have longer lifetimes and how I can make sure that the prediction of that lifetime is more robust and more accurate. And also, since we talk about lifetime, we assume that the canisters will fail one day, so they're not forever. But how do canisters really fail? I think it's important to take a step on the side to look into this so everything that comes later is a bit more clear. So in a rather dry performance assessment language, we say that the canister will fail when the environmental degradation of the materials exceeds a certain threshold, which is defined by the mechanical stress in the repository. Right? So it means you need to have both corrosion and mechanics acting for the canister to fail. And it also means that you need to look into the interactions between these two processes. And some examples here of, let's say, credible ways of different canister concepts would eventually fail. So you have a nice metallic canister that corrodes uniformly, and its wall thickness gradually becomes smaller and smaller until it reaches a certain thickness that can no longer support the lithostatic stress, and the whole thing collapses plastically, right? Or you have a steel canister that you have welded shut, and there's a defect in the weld. In the beginning, everything is fine because the defect is small enough that it doesn't cause any fracture under the external stresses. But as the canister corrodes, hydrogen is being produced, which makes the steel more and more brittle until a certain point you make a fracture and the thing breaks. So there's always chemistry and mechanics coming into the equation and into the process we need to understand and to predict. What kind of canisters are out there? So I don't expect you to read all of this. It's just a few examples I will walk through. So these are the waste management organizations that are participating in Concord. They're basically major European ones, plus Canada, plus Japan. And what is interesting to see is the second column where you can see the canister concepts. And what you will immediately see is there's only two canister materials in question, either steel or copper. Everybody uses the same two materials. And the next column gives you the expected canister lifetime. And you can see that for steel canisters, it varies between a few centuries and a few thousands of years. And for copper, it goes above 1 million years. So there's your first optimization. Canister material can increase your canister lifetime by 3 orders of magnitude. All the other columns give some information about the different chemical and mechanical parameters that will eventually lead to the failure of these canisters. And if you look through them a bit quickly, you will see that there isn't much variability. There's some outstanding cases, but general things are rather uniform. For example, you can see in the second to last in the dose rate, pretty much every canister concept is below 1 gray per hour, except Andra and Ondraft that they are just a few gray per hour. Here's another table that shows you how different WMOs that have a copper-based canister under consideration have treated different corrosion mechanisms in lifetime prediction. They're all the same, right? One point for SKB that used allowance for the microbial activity prior to buffer saturation. Everything else is identical. We're all doing the same things. This is the same table, but for the WMOs that have steel canisters. Here it's a bit more variability, mainly because we have very different buffer and near field conditions, especially Andra that has no direct buffer and Ondraft that uses cement. But the other two, Nagra and Numo, that have steel with bentonite, they're pretty much identical. So we all use the same two canister materials, and we all use the same approach to predicting the lifetime. Suspicious, no? Well, no. It's not suspicious because it works. The reason why we all do it like this is because we can build canisters from steel and copper that are safe enough today, and by following this approach to lifetime prediction, we can convince other scientists that we know what we're talking about. It's as simple as that. The question now comes, do we all have to do it like this, or is there a possibility to do things in a different way? And I would like to go through some examples of showing that there is potential to optimize, and there is potential to make canisters better performing and more robust. First thing, obviously, is materials. We already saw the steel versus copper debate, and there's a wide range of materials that could provide longer lifetimes. Generally speaking, they are limited by our ability to manufacture canisters by these materials and by the fact that they're rather new and we don't yet know their long-term properties, right? Titanium is used for less than 100 years, but iron and copper for thousands. Simple as that. But even not going into comparing very different families of materials, this graph there shows you the effect of slightly modified steel composition on the fracture toughness of the material in presence of hydrogen gas. So the example we saw earlier of the steel canister that slowly becomes more and more brittle. So if you look at a gas pressure of about 15 MPa, you can have fracture toughnesses between 40 MPa root meter up to 100. So only tiny differences in the same family of materials can make your canister twice as strong. Another very good example is all the work that Andra has done in selecting a stress corrosion cracking resistant material for the canister. Basically, by choosing the correct material, they have completely eliminated this cause of environmental degradation from consideration. Another example is the actual design and the shape of the canister. I know you're already thinking they're all cylinders. Yes, but there's intricacies that we can take advantage of. So we already saw a photo, and I think you all seen a copper-coated canister, how it looks like. It looks like a pill, right? So it's a cylinder with hemispherical lids. And the reason why it looks like this is because thin coatings don't like edges and corners. It's a stress concentration place. It's the place where the coating will fail fast. So you're forced to make the canister with a smooth outer surface. When you do that, you realize that by changing the shape of the lid from flat to hemispherical, you completely change the stresses at the weld region as the external lithostatic or hydrostatic load is applied. And what this allows you to do is to change from a 14 centimeter deep weld when you have a flat lid to a 5 centimeter deep weld when you have a hemispherical lid. Coating or no coating. Obviously, this is much faster to fabricate. It's much easier to inspect, and it has much slower propensity for flaws. So you can make your manufacturing process faster and your canister stronger and more robust, just by changing the lid shape. Another example is the manufacturing process. There's a lot of potential for optimization there. The one big thing that has, let's say, come to the forefront the last decade is the fact that we are started to consider coatings more and more seriously. Coating a container is a very efficient way of creating a canister that has two materials instead of a single one and provides various benefits, but of course new challenges compared to what we were used to before. We have to acknowledge a decade of work by NWMO on developing the copper coatings and demonstrating the feasibility. There's been quite a lot of interest from other countries in similar concepts, and basically by showing acceptability of one coating, the door is now open for us to explore or to reevaluate other coating materials and processes that could benefit canister performance and its lifetime prediction. All these three concrete examples were tailored to canister lifetime, but there's many other aspects of a canister that you would eventually consider to optimize. First thing, operational aspects, right? Shielding provided by the canister for the people working on the surface facility, or how well it would survive a handling accident. Inventory and canister loading, how many fuel assemblies do you put per canister? What's the optimal number there? Criticality, heat production are things that you would like to optimize there. Of course, cost and procurement, we can decrease costs for sure, and we already saw from the presentation from Posiva that having several suppliers is a very important aspect when you are ready to actually produce thousands of canisters. Maybe not at the research stage, but we will all eventually get to have to answer that question. Now, we looked at optimizing canister lifetime. The other open question is, how do we optimize or improve our ability to predict that lifetime? And this rather rough flowchart shows you how pretty much all of us do our lifetime predictions and why they all ended up the same when we're looking at the tables before. So you start from the top left, and you have your input parameters, which is the canister design, the material properties, and how the environment will evolve. When you know all these three, you can assess which chemical and or mechanical degradation modes this system will eventually see. From those processes, you have some processes that are unlikely to occur, and for those you need to provide arguments based on something, design or properties or environment. And there's some processes that may actually occur and lead to the degradation of your canister. For those processes, you need to demonstrate that the effect is both minimal and predictable. And in order to do this demonstration, in order to do this prediction, you have a number of tools at your disposal that are shown there in the furthest right. You can do mass balance calculations or mass transport limitation, kinetics, mechanistic arguments, etc. Right? So this is how we end up predicting how long a canister will live. And of course, the keywords here are provide arguments and demonstrate predictability. This is our output. This is what we use to convince people that we know what we're talking about. And in order to provide better arguments and to better demonstrate that we're able to predict, we need to know more about the chemical or mechanical degradation processes, and we need to have better tools in our disposal to do that prediction. And these are basically the main aspects where Concord actually comes in and tries to improve. So from looking to what we could do, let's see a bit about what we are doing already in this respect, in canister optimization. These are the opening, let's say, the foundational statements for Concord. Spent fuel canisters that are safe enough and feasible exist today, but can they be optimized, and can the prediction of the lifetime be more accurate and robust? And Concord is doing work in three of those aspects. Right? First of all, in trying to make more corrosion-resistant or longer-living canisters, we're looking at materials properties. Right? We want to explore the potential of new container materials to optimize the canister lifetime. And this is some examples of work actually ongoing in Concord. A big problem, I mean, for many people, ceramic canisters would be perfect, right? People think they don't corrode. That may not be true, but everybody expects to be chemically inert. The problem with ceramic canisters, or one of the problems, is you can't seal them. It's very difficult to weld. And some work that is going on into Concord is looking exactly into that. So you would have a kind of canister, like you can see there on the top right, is a prototype from Andhra. You would use a sealing material to put the lid on the main body. And in order to do that, you need to heat it. What we are doing there is trying to optimize the sealing material you put between the two pieces to make it more reactive to microwave heating to allow the two pieces of ceramic to be sealed together. And you can already see that with some nanoparticle functionalization of the sealing material, we can get up to 1000 degrees Celsius at a heat input of 80 watts. So pretty good improvement. If we are able to solve this, I think people may reconsider the use of ceramic canisters. Another area of work is the coatings. I already, I think, expressed my enthusiasm for coatings. There's some work being done there, either optimization of existing techniques or techniques that are actually used widely. For example, the cold spray of copper. We're trying to improve the adhesion of the coating to the substrate by including some alumina particles in the copper. Or we're also exploring, let's say, alternative techniques and materials that are used in other industries but have not yet really been considered in rad waste management. For example, physical vapor deposition of titanium, chromium, and copper. You see some examples of samples already produced on the right-hand side. The other major area where Concord is trying to make a step forward is understanding the processes that lead to canister degradation. In this respect, it's basically improving system understanding and providing mechanistic understanding of what really will go on. In this respect, we have isolated 3 processes that are rather complex and coupled and tackle those. One thing is corrosion under irradiation. One is microbial-induced, the other one is microbial-induced corrosion, and the third one is material degradation during transient. So while the environment in which the canister is exposed to is changing. I pick one example here, which is the first one, in irradiation-accelerated corrosion. There's been a quite, let's say, well-known open question in the literature about how exactly are you able to calculate and predict the effect of irradiation on corrosion. You can do one thing like the plot on the left, which shows pretty much the corrosion rate versus the total dose that your samples have seen. Very clear, you can see the dots. The higher the total dose, the higher the corrosion rate. Looks pretty straightforward. But if you look on the top left, the dose rates that were used for the experiment, first of all, they're much higher than what the canister will ever see, from a few times to a few orders of magnitude. Plus, in order to keep the experimental duration reasonable to get higher total doses, you need to use higher dose rates. And the plot on the right is exactly the same data, but plotted between corrosion rate and dose rate. It also increases by increasing the dose rate. So basically, you are forced to change 2 parameters at once, and you're not able to identify which one is the important one. When you know, you can design better experiments, and you can be less conservative in your lifetime prediction. And this is what we're doing in Concord. We're trying to tackle exactly this. This is the experimental table of a series of corrosion irradiation experiments. As you can see on the, let's say, x-axis, there's 4 orders of magnitude of dose rates that are being explored. On the, let's say, on the y-axis, you have the experimental duration. The number in each cell shows you the total dose. So 4 orders of magnitude of dose rates, 2 orders of magnitude of total dose, both on steel and or copper, systematically looking at what is the effect of each parameter will eventually lead us to a clear answer on how to incorporate irradiation corrosion in our canister lifetime assessment. The third and final, let's say, area in which Concord is working on is improving our tools for prediction. So there's a whole task devoted to demonstrating mechanistic understanding of the degradation processes and developing predictive tools for the time scales and repository scales of interest. So what we do in this modeling, pretty much mainly modeling exercise and integration for performance assessment, there's 2 kinds of activities. One activity is pairing a modeling team with an experimental team. So we have one team actually modeling and predicting the results of a specific experiment. This we will use as support of the interpretation of the results. And the other thing is integrating results from Concord, both modeling and experimental, for allowing people who do performance assessment to improve their lifetime prediction. This involves aspects such as extending models to repository scales or integrating new knowledge that was developed or will be developed in the work package, and strengthening the argumentation and modeling tools for performance assessment. which brings me to the end of my talk. I think that there are several aspects of disposal canisters that have big potential for optimization, and I think we should start looking at this quite seriously. The canister is one of the components of the EBS that will benefit the most, I would say, from the progress in science and technology in the coming years or decades until repository implementation. We will end up with canisters with longer lifetimes, and we will reduce our uncertainties and our conservatism in the prediction. We will be able, hopefully, we will be able to increase our confidence in making long-term predictions of canister lifetimes if we understand better the degradation processes involved and if we have better modeling tools. And Eurat Work Package Concord, which is now about halfway, has total duration of 3 years. We just finished our first year. We'll try to tackle these aspects. So look into new materials leading to longer canister lifetimes, improve our scientific understanding of degradation processes, and synthesize newly acquired knowledge in a form that can be used by WMOs to predict their canister concept's lifetime. Thank you very much.
Thank you very much, and good afternoon, everybody. Thank you, Nikitas, for this really interesting talk, and I would say perfect introduction to what I'm going to talk about. Just the order is the wrong way, because the project I'm going to talk about was before. So this project ended 2.5 years ago, and I'm really glad to see that Eurat is addressing this topic in such a systematic manner, and to see that there's really good progress in the question of designing containers and what are the requirements and what are the tools to demonstrate safety. So just a quick outline. We also reviewed the project started already 5 years ago, and as I mentioned, 2.5 years ago, we ended up with it. So it's a summary of this outcomes, and it is related to the specific German situation, of course. So we also started with an international review of container concepts, container-specific impacts and boundary conditions, which is really the essential part of designing containers. I will explain in a little more detail. Then what comes out of it is the derivation of requirements for the containers and considerations regarding potential container concepts. So I'm going back a little more to the scratch to say what options do we have in general, also referring to the existing concepts, but the question is not only the existing concepts and their adaptation maybe, but also do we have new ideas specifically addressing the specific waste situation in a certain country, like for instance Germany. And I will end up with some conclusions. I will also start with a conclusion, which might be a little surprising. So first of all, some general statements about containers, which are receiving the high-level radioactive waste. And sometimes it sounds quite simple to say, okay, put it in a box, make the box safe, close everything, and then it is. But it's very complex, as you could see also in the last talk. But it is a key element of every repository system. And especially if you are concerning different potential host rocks, like we have in Germany, not just granite, not just clay, but also maybe salt or rock salt. And disposal container design is decisive regarding the boundary conditions for the transport and emplacement, so the operation inside the facility, and of course the operational and long-term safety assessment. And the conclusion is here, the systematic derivation of the requirements to be placed on the disposal containers forms the basis for a targeted, for comprehensible, and what is also very important, transparent to everybody, to the public also, development of containers that meet the requirements. And this requirements is also a key element of this. This is just a short showing the project. So we reviewed lots of documents in a very systematic manner. I think something like the outcomes are very similar to what Nikitas was talking about. And here the summary of this, that most advanced programs for crystalline rocks are established in Finland and Sweden, of course. Also Czech is using such container concepts, claystone in France and Switzerland, as we know. We have open siting processes in Germany, UK, in the US also, besides Yucca Mountain. Internationally, which is, of course, which somehow logic, are largely the same protection goal definitions, especially in the nuclear area. The majority of the internationally considered concepts include some kind of robust containers, but very often they are not self-shielding or not complete self-shielding, so they need additional overpacks. And requested container service lives, as already were discussed here, up to 1 million years or some 100,000 years, and for rock salt in Germany, the latest was about 500 years. So coming to some kind of systematic approach, that's what we were thinking about. First of all, which is a little specific in Germany, we have a defined high-level radioactive waste, amount of high-level radioactive waste. So no further operating plants, so far no further operating, let's see. We have to look for or search for a repository. We don't know at the moment what it is, in which rocks or host rock formation. So we need the location, the concept. This is unknown, and also the container concept at the moment is unknown. But this together defines, of course, the radioactive inventory, the geology, the handling, the operational disruptions, incidents, everything what we need to consider, and which leads to mechanical, thermal, radiological, chemical, and biological impacts in the short term, in the midterm, and also in the long term to the containers. So this is a loop which is going to be closed. If we know these impacts in more detail, we can also design our container more directly to these impacts and the requirements. So some examples, I will skip these slides, you can read it later. This is also some data concerning temperatures, concerning radiation levels, concerning mechanical stresses. Then I will come to the next chapter here. It's a derivation of requirements. So first of all, we start with the basic regulatory requirements, which are atomic law, radiation protection law, site selection law, and so on. So some more, and also, of course, the technical rules and what is existing with relevance to this topic. And especially this disposal safety requirement ordinance in Germany, which is addressing this, differs in different utilization phases of the repository, which means we have the emplacement phase at the beginning. Then after completion of the emplacement of the containers until the start of the decommissioning, we have the retrievability phase, which means we need to be able to retrieve all the packages if necessary for some reason. And this is followed by the 500-year recovery phase. After the repository is closed, this is internationally somehow unique. So we need to identify the containers, and we need to be able somehow to retrieve them or to recover them until at least 500 years after closure. And then this is followed by the later post-operational phase until the end of the lifetime. And if you correlate these basic requirements and the disposal containers with the utilization phases, you can identify which requirements are relevant to which phase of operation of the repository. I don't want to go to the details, it's just to show you how we did this approach. And this comes to this scheme of an approach. So starting with the regulatory requirements or the requirements in general, you have to identify first, then you have the host rock and the utilization phases. You can identify the potential or possible impacts on the disposal containers, depending on the phase of operation. And on the other hand, you have the specific container requirements. And with that, you can develop containers. In this stage, it's very generic because you don't have the site, you don't have the exact container design. This is the first step of an approach which you can extend. So we did it here. You see the slide before is just now on the left-hand side. And then you come to potential host rock formations. It is more concrete already. And you get more and more close to the final site. And with that, you get the concrete data more precisely. And you can also, at the end, design your container concept, the entire repository, of course, but especially also the container concept. And with that final container concept, then you create or work out the safety case, and you go to the licensing procedure. This is the scheme of this so-called top-down approach. Here in general, you come from the generic to the host rock type, to the repository region, and finally to the concrete site where you want to place your repository. So if you bring this together in a few words, the container functions, you need to meet the requirements under the given impacts. So that's what you need to know. And then our question was, we have also existing containers, existing container concepts. Can they be used? Are they able to fulfill these requirements? Or on the other side, we have or can develop new container designs or concepts. And this is a question, existing container concepts with some specific adjustments. And if you compare this, what we started in a very rough way, not in detail, you see it here in this scheme. You can compare the reviewed international container concepts, what Nikita explained in much more detail. So this is what you can take here. And you compare it on the possible potential effects and processes. The requirements, are they similar? Are they the same? Where are the differences? The derived container functions, and also to elaborate generic container concepts from considering also the existing international container concepts. So the conclusions regarding these existing container concepts, the outcomes from our discussion in the project were, to date, mainly generic container concepts have been developed. This is not really true because in many cases, or some good examples we have seen, there are well-established container concepts which are going hopefully closely into operation in the next years. But this is specifically to the repository environment in the specific countries. So far, usually qualitative statements based on hypotheses and argumentative considerations have been prevailed. This is meant not to the specific well-developed programs, but in general in the international scope. And there are many countries which are on these stages. They are discussing basic concepts, but they are not really detailed. And this is this has to be improved in the future also, and it will be improved. And significant gaps regarding knowledge is also need for further R&D work, and this was very good to see what Eurat is doing here with the Concord project. I think this is a very valuable approach, and I'm really curious about the outcomes of this project at the end. In Germany, we are also discussing transport and storage containers to be considered as potential disposal containers. And here is are really significant questions concerning their long-term performance and also the handling, and what needs to be done to maybe improve them for final disposal. And what I mentioned already, the requirement for recoverability, about 500 years exists exclusively in Germany and has not been considered for any container concepts. This has to be evaluated if container concepts fit with this requirement. With that, I come very briefly to the development of generic container concept. This is very, let me say, theoretically, not in a specific way. So we have the container functions to meet the requirements under the given impacts. This is somehow the slogan, let me say. You can split this into partial functions of containers, what they have to fulfill, so safe enclosure, shielding, heat transfer, and so on. Mapping these to generic container components, you have the walls, the lids, trunnions, whatever you need for handling operation. And then you can derive technical or physical solution principles for filling the partial functions through the container concepts. And if you bring this together, you get a broad range of opportunities. So this is really very complex. You can create lots of things, lots of materials, lots of potential geometry maybe. And with that, you can derive many or various different container designs. This is not very convincing usually because you need to narrow down. And this leads to the conclusions that you can split it into all these separate functions and components, and then you put it together, and then you get a specific container at the end. But not every free combination of the solution principles offers an equally good qualitative or quantitative fulfillment of all requirements. Interactions must be taken in account. It makes it even more complex. And what is important, the optimization process, and that's what we are discussing a lot here about optimization, includes weighing of partial functions and availability of materials, manufacturing costs, and so on, and which leads also the need to include trial and test programs. So what is really available, what makes sense, and this can be weighed and valued and included or needs to be included in this optimization process. But anyway, the systematic and comprehensible optimization and narrowing down of suitable concepts is of crucial importance. And this requires a systematic derivation and presentation of weighing factors and optimization processes, especially when you're going to discuss your solutions in the public or with the public in the process, and you want to convince why you want to use this concept or not the other one, because there will be a lot of discussion about excluding some kinds of materials or some kinds of concepts, and this needs to be really good or presented in a very convincing way. So the main conclusions, and these are going to be my final slides of the presentation, the developed top-down approach enables a systematic derivation of suitable container concepts as part of the site selection process. And this is addressed specifically, of course, also to the German situation. The basis, therefore, are clearly defined requirements. They need to be identified. Site-specific impacts, and as I said, with its top-down approach, from the more general to the more and more specific, and the derivation of a methodology for determining selection and decision-making criteria for suitable disposal container concepts needs to take into account the requirements for transparency and the time frame of the site selection process also. So science is able to do a lot, but this takes time. And I think we need also to think about time. In Germany, we have a date in our atomic law, which is 2031 for site selection. And I think in some time later, there should be a repository in place and get into operation. So we cannot invent the wheel from the beginning. First assessment of the suitability of container concepts that have already been developed. So we have nationally the Pollux concept for salt, internationally concept transport and storage containers, as I mentioned. And in all cases, we found out that significant adjustments and further evidence are required. And the other aspect here for us is also the temperature limit, which was narrowed, lowered down to 100 degrees C at the moment. For salt, it was 200 in the past. And so there's a question, can we increase it again? Because this is limiting also lots of container concepts, especially for the salt, what has been developed in the past. The demand for recoverability is associated with open questions for all the container concepts because this addresses or is related directly to the long-term performance. And as I mentioned already, so this huge variety of potential container concepts needs to be narrowed down by a convincing approach. And our general recommendation we ended up in the project was that against the background of the time frame and the site selection process, preference should be given to robust container concepts based on materials and manufacturing technologies that have been already developed and tested, and which can be manufactured reliable with the required quality and on time in large quantities required. So this makes the loop complete somehow to what we were listening before. And with that, I will also add that there have been some recent developments. So BGE is now responsible for the development of the disposal containers. And BGE has already awarded a project for the development of disposal container in crystalline rock. And for the other host rocks, projects are also on the way. So with that, I would like to thank you for your attention. And if you have any questions, please.
Dear Symposium audience, I'm happy to be here and continue the story which started by Tina about the optimization. And I'm trying to give some practical examples about the clay components. And then it will be continued tomorrow by Anne, then from the safety case point of view. And I have to say for the Nikitas and Holger that actually you do really need the clay people and the clay while to ensure that the canister has a nice and smooth stay in the deposition holes or in your concept. And the presentation I'm giving now, so I'm prepared it together with Ville Heino, who's the program manager for the buffer backfill and closure program at Posiva. Yes, let's start. Yeah, as we have heard many times today, and you all does know that our concept is based on the KBS3 direct disposal in the crystalline host rock. So I'm like telling you about the buffer backfill and deposition tunnel plug status a bit, while those are the components which we do need in the near future within the coming years when the disposal actions aims to start. And then also slightly about the closure, which then is more far away in the 2080s or somewhere when we are closing the first central tunnels. So, and my presentation is also concentrating on the man memory, or of course, I don't know how long the man memory is, but today we are talking about 10 years time. So at the time when we did submit the construction license application, and by like today, when we are still finalizing or fine-tuning the topics for the operating license and to preparing to the production or to preparing to the operating period. So and also I'm trying to highlight what is the management procedure, the change management procedure, and I'm using the deposition tunnel backfill as an example for that. Yeah. Our approach has been like the stepwise development during the last decades, and we have been doing pretty much the work together with the SKB. We have a lot of SKB people here as well. So we have been doing the joint projects and also information exchange. And also during the 6th and 7th framework programs, Posiva was actively participating to the ESTRED, LUCOEX and the DOPAS project projects. So in that sense, that like, but pretty much our demonstration and test program has been done like with our own forces and within the POSIVA program. So what was actually the status in the construction license application? So then 10 years ago, we had the buffer consisting of like the cheese shape big blocks, and also the big pineapple rings, and this tiny tiles for the chamfer. And the chamfer, of course, is needed to be able to install the canister. Then our backfill did go in the deposition tunnel did consist of blocks and pellets. And then we had between the backfill and the deposition tunnel block, so there was the seal layer, and that was also consisting of like small tiles, which were like installed manually pretty much. So that was the status in our construction license application and in construction license as well. So then we had to test that the system does work, and the test phase was making in steps. So first we had like the component by component testing in the different projects, as as showing here. Sorry, it wasn't not so easy. Yep, here. And we did move into the full-scale in situ system test. Well, we did test the whole concept together. And the next phase, what we are actually doing is the trial run for final disposal. And after that, so we are mature enough to start the operating period. And actually here is around 5 years gap between the full-scale in situ systems test and between the trial run, and pretty much the changes what I'm explaining today has been happened during that 5 years period. So during basically the last 5 years. And what has been changed then? Yes, there, of course, many things. A little bit. Some of them are bigger, and some of them are a little bit smaller. So we have a new backfill material. We have a new manufacturing method for backfill. And then we have also like the segmented buffer that was already actually tested within the full-scale in situ system test. Our block design has changed in slightly, and also we have the new closure design, and the requirements for the closure has been changed for that part of the tunnels. Otherwise, we can say that pretty much the requirements are the same as they have been, so we have not been touched them, but except we have the systematic requirement management system, and the performance targets are the same as they have been, but then of course the design specifications, which are like the most practical level, so there has been changes. Yeah, if we start from the buffer, so now current design for the buffer consists of these segmented blocks. And that's, as Tiina explained in her presentation, so basically the reason behind was that then we have more options to manufacture, and maybe it's easier to purchase the components when there are more variability for the suppliers. Then another important thing for the buffer, Tiina also mentioned that, and was that we had the really tight tolerances. And now when we are using the granules instead of pellets in the gap between the rock wall and the blocks, so it means that we have a higher density, and then that helps us to make a little bit like more uneven whole from the construction point of view. So there are like the three boundaries which are like eagerly discussing with each other. There are like the construction people, there are the machinery people, there are the clay people, and of course, yeah, still the canister people, and all of those has their own needs, and we have to find the joint solution to make all happy. But then it means that one of these parties maybe has to take has to do more work or has to pay a little bit more, and then the sum of them will save money and maybe do less work, and then that's the company level decision that who actually has to work more and how much, and then we have to make it via business case. So that's actually is the life what we have been experienced and currently are also discussing for some like a minor things. Yeah. Then if we go from the buffer into the backfill design, so there we have maybe a little bit bigger changes, and now within LUCOX, so the FE experiment run by NACRA has been really like how to say example for us, and we have been following that, and we have been getting really nice support from NACRA. So thank you all people. Here are a couple of persons working with the concept, but all of them are not here today. So but we do really appreciate that we did receive nice hints from you to apply the backfill concept then to our like conditions. So the fact was that we did note it when we were doing the full-scale in situ system test that our backfill blocks and pellets for our needs and for tunnel dimensions was not the best or the optimal solution due to capacity and due to some other topics, which does not exclude that someone else could use that well, but that was like from our like operating point of view. And for example, like the amount of the materials, like plastic covers for the blocks and so on. So that was maybe that wasn't that sustainable. So using the bulk materials for as the granular backfill is, so it's much more appropriate like material. And yeah, so there were like a lot of discussions how it was handled within the POSIVA, and I will show you that. Then for the deposition tunnel block design, so we actually didn't make too many changes in the design, but we changed the safety classification for the block block, how to say, the structure, which means that the inspections are more easier. We don't have an external organization doing the inspections for us, but we can do them by ourselves, and also we did to move like the hydraulic conductivity requirement from the concrete part into the backfill part for the ceiling layer. And since the backfill was changed, so that goes, of course, like change then in the shape of the seal layer. Yes, and then for the closure design, of course, when it will be implemented in the far future, so we are not as detailed as for the other like clayish EBS components, but here as well our design was changed in the way that we did add the cross-struck material into the bentonite. So the revised requirements allow to do that, and then in the same way, so it's a bulk material, it's easier to handle. Some part of the material we can purchase from Finland, and we don't have to make too much logistics or transports, and also yeah, we have been doing in small scale like testing even the installation methods, and we have been noted that that's a workable option for future, and we can live with it in this stage. Of course, we do need the also the closure design for the operating license application, while that's one part of then the safety case work that we had the requirements available and also the design available. And of course, it was also the cost issue. Yeah, then I promised to say how the change management in our organization proceeds. Here it looks really easy and simple, but actually it's 5 years work and includes many steps and also like the project wasn't. It was quite an extensive project with it, but yeah. So everything was initiated that we noticed that the block and pellets perhaps requires maybe more efficient method. And then within our organization, we were asking for the guiding decision from our, well, like internally from Posiva, from our like operating management. And that's handled in many phases. So we did request then like different type of statements from the long-term safety, from the different other boundaries, and like it required the project there behind. So they made prototype machinery to test the materials. They make the prototype or trials also to manufacture the material. There was the performance like work done behind, lot of modelings and tests and experiments for the THM. For the TH, for the buffer backfill interaction, for the like erosion, chemistry topics, and still a couple of more. So that's a part of the work was done before the decision was done internally, and then the work did continue and actually is now on the finalizing phase. And then currently, so we are already manufacturing the actual machinery for then the operating period, and we will test the granular backfill now above the surface during this autumn, and then the next phase is to make the tests underground as part of the trial run for final disposal. Yeah, so that's a very fast explanation of the change management, and Anne will then continue a bit of that then tomorrow. So I have mentioned the trial run for final disposal a couple of times. So I'm not going to the details now, but it's just for you to know that that we will then like install with the real machinery, the real components purchased from the real suppliers, with the real staff who are really working then below the surface and of course above the surface in the encapsulation plant. So that's I think that some of you are also like following the project. Yeah, but we don't have a time either to go into the details here. And hey, the story is not over yet. As Tina already said, that we too need the optimization into future and so on. So I would also say that the devil lives in the details, as is known. So now when we have been testing in reality, like our concept, and are still testing it without the fuel prior the operating period. So there are a lot of tiny things which needs to be still considered. And I'm not going into the details, but I think the Anne will touch those topics still a little bit tomorrow. Yeah, that was basically shortly the story of the clay barriers and the changes.
Thank you. So, maybe I should start with saying that, as they do in the beginning of some movies, based on a true story, sometimes during the presentation I will maybe exaggerate some things, but I will let you know. And I also have a spoiler alert. I will not talk so much about technology, rather organization and culture and mindset of the people working for us. So I think I have this one. So just to set the scene, you can read the facts and figures, but SKB started to develop the KBS3 methodology in the mid-80s. And of course, almost 40 years later, things have changed. And in 2018, when I started out at SKB as head of projects, at least my opinion was that the idea in the company was that we have developed it so good, so it was nothing to improve. It was really perfect, and it was really fragile as well, like a Ming vase. If you touched anything, then it would crack. But we had a situation in March 2020 when we did our new calculations for the final cost for the repository. We had a quite big cost gap, and I think all of you will during the process end up with that, because during so much time you have inflation and other things tends to increase in cost, and you will end up with a cost gap that you need to address in some sort of way. So that's more or less what I'm going to talk about, how we address that cost gap and how it ended up. So this is a picture drawn by our CEO, just to exemplify what kind of situation we had. So if you're a car manufacturer, of course you have a lot of requirements, safety requirements, emission requirements, and other things. So, but we could tick all the boxes for our solution except the cost, more or less. And if you're a car manufacturer and you cannot meet cost requirements, then you cannot sell the car. So what do? Do you give up, or do you go back and do it all over again, try to find new solutions? And that's what we wanted to address to our organization. Do we want to stop here and lay down, just quit? Or do we do it once again and try to find another solution to actually be able to come forward? So what we did, we gathered people from all over the company. We did 2 workshops. First we had an identification workshop, and the intention was just to gather all ideas that we possibly could have, go back to solutions that we have thought of earlier, and just get new ideas. And it went really good. We ended up with 237 new ideas, some of them big, some of them small. But we also needed to evaluate all of those ideas. So we gathered expert teams. We sorted all of these 230 ideas into different groups: construction, rock excavation, maybe bentonite and clay production, and gathered experts in those areas so that they could evaluate all of these ideas in their box out of 7 different categories. Everything from safety to how feasible it was, to how much work do we need to put into it to actually make it happen. And we also, from that second group of workshops, we sorted all ideas into 4 different boxes. The first one is new decisions. Can we take a decision already today? Do we have all the information needed to actually go in another way? Take on that kind of solution. The third box is, do we need, of course we need new decisions, but do we need some preparatory work, some investigations, just to be sure that it's feasible? And then we also had a box for potential future decisions. And of course, we had a lot of ideas that we put in box 1. We have come too far. We cannot back too much in time to actually, it's a good idea, but it's not feasible where we are, what kind of situation we have today. I think I skipped this one. It's just some rules that we have for the identification workshop, just to make people be creative. So we ended up with this result. The CEO required that box 3 and 4 needed to be as big to address 2/3 of the gap. Otherwise, we have to go back and do it once again. But we did actually with those workshops. We ended up so that we could address all the 2/3 of the gap by doing this. And what we did after that, we started implementation of it. And we had a thorough follow-up every month on the progress of the work. And as you see, we have the baseline, the blue, what we set up when we did the evaluation workshops. Some ideas in the beginning didn't end up with as high potential as we thought in the beginning, but then we have other ideas later on that ended up with bigger potential than we thought. And in the end of the almost here in the end of it, we actually exceeded what we thought initially. And working like this, we also created a culture in the program to really think of new ideas, to be creative, to think of new things, new ways of doing things. And we ended up with new ideas during the process as well, the evaluation process or the implementation process. So just give you some examples of what we did, some of the bigger ones. We looked at the above ground buildings. In the beginning, we set up a requirement that said that we should have one building for each function. But we challenged that and said, why? Is it really important for us? It's not a safety issue. It's just something that we said. So challenging that, we reduced the number of buildings from 20 to 6 buildings. And then we also reduced the need for landfill, the environmental impact, landfill of a bay, and that kind of thing. So 40% reduced area that we needed. And we also increased the flexibility. If we had larger buildings with several functions, if things change over time in the future, we are able to do changes in those buildings. If we had one building for each function, then it would be we would be stuck with that. One other thing that we looked at was the logistics of the bentonite sourcing strategy. We had an idea that we should source large bulks of bentonite, and then we had huge storages close to Forsmark, and then transport by smaller boats into the Forsmark harbor for our needs. We challenged that as well and said that let's purchase smaller bulks, have smaller storages, and put it right away on site in Forsmark. And that reduced the initial investment quite dramatically. On the other hand, we have higher operational cost, but in total, it's a quite large saving doing that. And the last one, I think Johanna talked about it yesterday, so I don't go into details, but going for segmented buffer pieces rather than a whole ring, that reduces the need for extremely large press equipment, over 200 tons. And you can imagine that kind of building, what kind of reinforcement you need in concrete and that kind of things. If you reduce the weight of the press and the investment cost will reduce, but also the investment for the building and everything around it. And it's easier to transport as well. So That's also a dramatic cost reduction doing that. So my final slide, the benefits of it. It's we all have heard yesterday, and you all know it, we have projects that tend to be for decades. And of course, people come and people go. And you lose the, if there's something that you decide early in the process, if people leave and get new ones in, you don't have any ownership for that kind of solution. You don't have the history with you. So by doing this, we strengthen the ownership for the new ideas, for the actual design that we have today. We got a really positive energy to be gathered and focus on one single item. I forgot to say that in the beginning. We said that this is really prioritized in the company. Drop the pen and everything you do. Everyone will focus on this for the identification workshops and the evaluation workshops. This is top one priority. We need to do it now. Because if you do changes when you have gone into construction, everyone knows that's a lot of change requests and it costs a lot. It's better to do it now before we go into construction. So that's why we wanted to address that at the time that we did. But we also establish a pride and a culture to optimize the solutions. And that's one of the good things with the thorough follow-up. You can see the results, and that's created by the employees that work with the idea. So that's really a strong commitment to that. And of course, you should be proud. It's a lot of savings that we do. Some learnings that assumptions that you do early in the process, they can easily become facts later on in the process. We have experienced that quite a lot. Things that we thought that we couldn't challenge because it's really requirements. But then when you look back, it's just an assumption somewhere in time. As you saw, 237 ideas. You just need to release them. They exist in the organization. Just let them release it. And let the team be accountable for the solution. I think Heinz talked about that yesterday. Take responsibility for your area of expertise. That's really important. And strict follow-up in time, because that makes it happen, really. So that's more or less what I intended to say. Thank you.
Good morning, ladies and gentlemen and friends. It's nice to see you here in the second morning. And I'm going to share with you a bit about the optimization work that's been going on in the pre-disposal aspects in waste management, the sister project to ERARAD, which you heard some snapshots from yesterday, as well as some of the posters. So many of you come from advanced programs who also have waste management in a pre-disposal for years, for decades. And you might even question, why would the EC be funding a project like this? We know what we're doing in waste management. But there's always room for improvement. There are new technologies that are coming and ways that we can continue to improve also in the pre-disposal side. And that's what I would like to touch on today. And also try to bring that into what does that really mean for disposability and the vision of IGD-TP as well. So I present on behalf of our whole consortium. My name is Erica from VTT and my co-coordinator Maria. And also I really acknowledge and appreciate the many contributions from our work package leaders. So a little bit about pre-disposal. It is definitely something that's well known. It's good guidelines already established by international organizations like the IAEA and the NEA, but really looking upstream, taking where are the wastes from operation, maybe from decommissioning, from other industries, and thinking about what do we need to treat, package, store, and get ready for the disposal step. And I think in the current day and the environmental sustainability drivers that we also have, these issues of pre-disposal become more and more relevant, strictly based on the waste hierarchy. The image on the right is from the UK, and looking at the number one idea is to prevent the waste in the beginning. If we do have the waste, we need to be able to minimize it. after minimizing it, we think, how can we release it? How can we recycle it? And ultimately, you may have some waste that you need to dispose of, high level, even in the aspects of spent fuel. But overall, the idea, of course, is to reduce the amount of wastes, and anything that we can do in the pre-disposal phase, in processing or better treating our waste to get to clearance or to get to a lower category of your disposability, to conserve space, to have lower radionuclide inventory for our environment is going to be a great improvement for all of us and for our world. And the predisposal really ties to ERARAD. These are not two separate things. Predis is an integrated part of the overall joint program of what we strive for together in this community, within also the vision of IGD-TP. So predisposal project, it fits in theme 2 of the ERARAD roadmap. And if you're not familiar with that, then please come chat with any of us or see some of the posters that are about the guidance documents and the roadmap of ERARAD. And Predis themes that go into this roadmap of ERARAD are directly based on the guidance and the discussions with the IAEA. So we look at the planning phases. How do you assess your inventory and the technologies, the waste acceptance criteria, and this waste hierarchy or sustainability mindset? Then you get into implementation of these technologies and treatments, characterization, conditioning, storage, and transport. How can you optimize each of those phases to make it more efficient when you get further into the chain? So for instance, how might you change your packaging so that it can go to direct disposal? How can you change your processing or improve your processing in a treatment or in a mobilization, which might make it safer in the repository? And then of course, when you're operating a pre-disposal facility, your treatment and characterization of the wastes, you should always be open to new ideas. If you change, for instance, from bitumen to cemented waste, or even in the future, could we look at geopolymers? Should we look at optimization to use thermal treatments to reduce the volumes? Yes, we might have a stronger concentration of the radionuclides in the residual secondary waste, and we have to treat that secondary waste also and be aware of the whole footprint of our solution. But trying all the time to think, even through the operation of a pre-disposal facility, how to optimize it and get it safer and more efficient for the disposability, and those go hand in hand. And then we also talk about the whole program. So though predisposal is kind of theme 2 in the roadmap, we have to think even upstream. How can we communicate to those who own the waste or who produce the waste? Not just a nuclear power plant, but some other type of norm waste or hospital waste. How should they sort the waste? How should they classify the waste? Can it be consistent better across our member states so that we can have shared facilities, so that we can have common understanding of how to package, how to treat? So trying to also talk to the people that are upstream in the waste owners and the generators, so that after we predispose, handle it, it's going to be better and easier and more sustainable mindset towards the disposability. And this whole chain to go from upstream to downstream is where we see is very important in this predisposal community to link disposability up. So some little facts about the project. These are in the slides, you'll get them. We have 47 partners. We have a budget of about 24 million. We follow the ERARAD principle that it's co-funded. That was by our choice. EC put money on the table, and we said we want to make sure that what we do is important and has impact for the whole community, both the waste generators who have to treat and process the waste, but also for the disposal community. And therefore, we also follow the principle of the joint funding to really look at identifying and developing and improving these technologies in pre-disposal. We admit they're already out there, but we see that there's room for improvement. Just to frame the project, we can't solve everything. We didn't get 100 million. We have a budget of 24 million, and we went through really strong scoping and discussion with industry, especially via the SNE-TP nuclear technology platform. Sustainable Nuclear Energy Technology Platform has one technical area, number 5, focused on decommissioning and pre-disposal waste management. And that is where the nuclear power plants are part of that organization, similar to IGD-TP where the WMOs are. But that SNE-TP forum is an important location where we hear the feedback of what do they want. And the decision at the time of planning the project was to focus only on low and intermediate level wastes and to pick these 4 types of wastes: metallic wastes, liquid organics, solid organics, and cemented wastes, which mostly deals with packages and brings in a lot of issues on digitalization and decision-making related to performance prior to disposal. So aging management, monitoring systems, decision-making, digitalization, and I think some of that will be touched on in one of my slides, but also covered by the next presentation. And the majority of the project is really, really focused on this treatment and conditioning, optimizing how do you treat and condition. But in order to do that, you have to also characterize and classify your waste. And then you have to model and understand how it's going to perform in the long term. And we also see, in order for the industry to accept these changes, that they need to understand the sustainability and the cost. They have to see that the economic and the environmental is comparable or improvement from what they have in order to get the buy-in and the investment also from the other stakeholders, even the regulatory, to accept these. So that sets the stage of what we set out to do, and we admit there's many other things we could have done. We didn't, for instance, touch graphite because there's other initiatives on that, and we recognize it's important, but it was something that we thought was, when we needed to bound the project, that we take these topics for now, where we thought we could make the greatest impact with this budget and the consortium and the time schedule that we had. Very early on when planning the project, we felt it was critical to have key performance indicators. This project, because predisposal already exists, we had to say, what are the drivers? Why do we do this work? And what do we strive for? Okay, we strive for cooperation. How do we do that? We strive for making sure that what we're doing can be adopted by industry. We want to foster cooperation so that we're doing things that, yes, of course, someone might do it alone, but we see that it's 1 + 1 is more than just 2 if we can share and do these things together. We have human capacity building. We need to train the next generation of experts. And so we had KPIs related to that, and also strong KPIs associated with having collaboration with ERARAD, with the end user groups, with SNE-TP, with IAEA. So from the beginning, we set very numeric KPIs, some which we can influence and some which are from the outside world. And we have exceeded quite many of these already, even at the halfway point of the project. Again, project structure, if you're curious, normal structure. A little bit simpler structure, I'd say, maybe than what the ERARAD joint program is. We have the 4 very technical work packages. They make up 80% of our budget. We do have some strategic studies, which I'll get to in a minute. I'll show you a slide about each of these work packages. And we also, again, have knowledge management, which is coupled very closely in cooperation with the ERARAD project. We do have a strong group of end users, and I'll touch on that in a minute. But I'm also proud to show that we have over 1/3 of the resources in the project have been female for the first period, and a pretty active engagement equally across all of our partners in that aspect. So we are at the halfway point. We planned the whole project in COVID. We never saw each other face to face when we planned this project. And for the first 2 years, we didn't see each other either. And that meant that we embraced the digital domain. We've had 15 public webinars with over 1,500 different participants, pretty much from around the world. All of those recordings and slides are available on the events webpage. We've already produced 17 deliverables, which are public, and you can download on a range of topics. Some of the most recent ones are listed there. We've been very strong to activate mobility. We feel it's important to have this cross-border cooperation and motivation and learning from doing together. And we've also activated 3 of those in support of Ukraine for the Ukrainian partners in our group. And then we've really fostered this younger generation, hoping that we can motivate them to stay in this field, keep this optimization of the human capacity building, ensure that people have a chain coming into their industry. We've also checked, how are we doing? We've self-reflected and shared this together also with the ERA-RED project as we look forward into the future about what are we doing and where should we focus on as we keep moving forward. Again, I'm not going to read all of these, you can read yourself, but I think it is important that we do this kind of value assessment, as we just heard from Escobe, to understand, where are we, and not just at the end of the project, but what should we work on improving, especially as we get to where are we going to go in the future as well. So then a little bit about industry, and we appreciate that many of you who are in this room are part of our end user group. It's very critical to hear, what does the industry need? What are we doing the right things, making sure that our project is on track? So we do have 25 different organizations who are part of this end user group. They do sign a confidentiality agreement, which means they can openly talk to us and tell us, you're doing the right thing, or we have this problem, can you help us solve it? And we're always open to have others there. So if you have an interest in this as a waste owner or a WMO, please be in touch with us. And others who are interested as research entities or regulators or civil society, those are a part of a stakeholder group which we engage with through these various webinars and such. And then we also strive for having great cooperation, especially with ERA-RED and some of the other projects, for instance, Mikado, which has been on characterization, and ERDO for the smaller inventory programs, where we see they can also really benefit from these issues of optimization in the pre-disposal phases. So then a few slides about actual technically, what have we been doing? What have we achieved? I'll go through one slide about each of the work packages, and some of these have posters outside, but I remind you, each of these work packages has a budget of 3 to 5 million. We could talk for an hour about every one of these, and there's other places where you can hear these scientific details. But within strategic studies is probably one of the key places where we try to assess, how is our project impacting you? How is it impacting the operations of the pre-disposal facilities, and how is it impacting the disposability, and how is it impacting what we should do together in the future? So we really make sure here in this work package that we're having good communication and understanding the who's who in the industry. We did an extensive gap analysis in the first year, where we gathered a lot of feedback from all different stakeholders to understand, what are the priorities, where are the holes, where do we see the best room for improvement and optimization in these pre-disposal aspects. We established a baseline strategic research agenda. Pre-disposal issues are touched on in many, many other documents that are out there, if that's from SNETP or IGD-TP, a little bit in the ERA-RED founding documents, but we gathered those and we compiled from around the world, where are the existing documentation of the needs in pre-disposal, and that is public, and we published it last year as kind of a foundation. And from that, we go deeper now. Where are we now, and what do we need in 5 years? And that's directly feeding into the ERA-RED SRA and hopefully the founding documentation for where we might go in the next 5 years together as our community. Within the strategic studies is also where we talk about issues on waste acceptance criteria. We work closely with the routes work package from ERA-RED. We look at what are the international practices on this waste acceptance which influence the pre-disposal issues. That definitely addresses also packaging and transport and interim storage, and what are the similarities and differences across these projects or across the member states in the pre-disposal WAC. And that also feeds into the newer project called Harper's, where there's a poster outside which talks about what might we harmonize in these issues and what can't we harmonize. We recognize that different people, different countries have different waste acceptance criteria, but why do we have those differences? And trying to help that we can facilitate better cross-border cooperation and cross-member state cooperation in the pre-disposal issues. It's also in this work package where we really deal with these costing and economic, LCA and LCC. And it's from this work package that we're working, I think, closest with ERA-RED in looking at what is the next step. So how are we going to continue to blend these programs together and work as one community of both pre-disposal and disposal hand in hand? So these SRAs and things that are upcoming and some of the guidance together. Here's a few extra slides about the SRA deliverable if you're interested in those kind of things. So we do have it close to being ready, and just a call out that there will still be a webinar in the first week of November specific to giving the final outcomes of what our SRA has been, and that will set the basis of the final chapters that go into the ERARAD SRA. Here is the story of what we have done so far. So this SRA has been a process over the past year, really trying to group and consolidate the results and reaching as many people as possible. And when we look at the SRA, we really worked on the example that came from the SHARE project on setting the roadmap for decommissioning R&D needs that had an established set of drivers. And so we went also through what kind of drivers there are. You don't have to read all of these. It's more to show you this mapping that we looked at all of these different issues that are in predisposal according to the roadmap, kind of the topics that are in the IAEA guideline, and understanding, are these drivers related to economics? Are they related to safety? Are they related to human capacity building? And we feel that, you know, doing good science comes along all the time with that. But what are the drivers of why you invest in predisposal issues? And the pie chart on the right shows the breakdown of the type of organizations who were replying. So we're also happy that we have diversity there, for instance, in regulators and governmental officials also replying for why do we do these predisposal issues and what do we need to do next in the SRA. And here's the secret. This is what people have been waiting to see. Where should we go in the next years? So what are the 5 most important topics? And a lot of issues still on this characterization and conditioning as really key places. Of course, making sure that we understand the waste acceptance criteria and how the inventory is. And of course, all of those things then impact how well you can dispose it if you have a better understanding upstream. But these are some of the details that will be in the SRA about where should we put our focus in the future in the technologies. Then last couple minutes here touching on some of the other work packages. Work package 3 is led by the colleagues at JRC, and really they're looking at competences, so at knowledge capture, guidance, helping anyone in the industry, not just a young generation, but someone who might be mid-career but coming over to our sector. Great yesterday to hear examples from tunneling and other infrastructure, and we need those kind of people too. So trying to provide guidance and signposting to preserve knowledge across the generations and help new members or less advanced programs make decisions in how they invest in predisposal waste management processing or treatments. So you can find a wealth of information on the webpage about different documentation and trainings. We've had in-person trainings and a lot of webinars, which we take also as educational purposes. We have a lot of students in mobility, and we continue to work very closely with ERARAD and trying to find new creative things to have wordly types of games, or to encourage someone to make a TikTok video about predisposal, because that reaches out to the next generation. So we really strive to ask the next generation and the younger generation, what do you need? How do you communicate? Let you self-organize. That we can give the right types of guidance to help you get your friends into this industry and stay in this industry. There is a lot of challenge out there on the job market, and we want to train people and we want them to get into this industry and stay in this industry and be motivated by being able to do great science and to see great practical experience with you in the repositories and in the facilities. So trying to keep them motivated. Then technically, because technically this is the core of our project. We spend 80% of our budget on the technical things, and I'm not a top expert in any of these. My job is in the coordination side, but I'm really happy that many of our colleagues from these work packages are here. So if you want to know more details, I'm happy to put you in contact, and there are a couple posters today in the lobby about these. So work package 4 is really focused on metallic treatments. You can keep in mind, for instance, a decommissioning where you have a lot of metal components, and if you need to put those into a medium level reactivity, Are there options to do better treatment to get it to a lower level classification or even free release? And again, that's country specific. In Finland, we can recycle and take our metallic components into the industry. In France, that's not allowed. So looking at ways to condition and treat the metallics to remove the contamination, but then when you do that decontamination, to understand, yes, you have a secondary waste stream. You now have a fluid that you need to treat that also. So are you making your problem better or worse? And what's the economics of that? And so those treatments, they can be new chemical technologies, they can be gel-based. As chemistry gets better in the world and new products are out there, we need to check, do they work and are they safe to go into the repository? And when you have that gel, can you treat it and can you immobilize it? And will it be suitable in the safety case for the repository? So this is really looking at ways to decontaminate and then how to handle that waste stream that results from the the decontamination. And when we look at those new materials, we have to understand what is their corrosion then with the rest of the materials. So how does it function in the package when you get ready for the disposability? Similar issue on liquid organics. So we have two work packages on organics, one being the liquid and one being the solids. The liquid is handled by CEA as our coordinator. And again, really looking at what are the ways to condition these materials, looking at alkali activated materials and geopolymers, understanding what are the challenges in the inventory, coming often from the plant operations and looking at new types of formulations with geopolymers, with metacholine, with slags, trying to reduce this environmental burden, avoid using cements if we can, and optimizing what types of materials we should use in treatment and making sure that if we do invest in these new types of materials, that they would be acceptable by a repository and a regulator in the durability and the lifetime in the safety case. Solid organics has a similar topics. This work package is led by SCK Sen. And again, this work package really came from the previous project, which was Theramine, that completed a few years ago within the EU program, where there was thermal treatments of wastes. But of course, if you thermal treat something by gasification or other incinerations, you have a residual, and how then do you handle treating that residual? So looking at upscaling of wet oxide routes, HIP, isostatic pressing, the immobilization wastes, and again, definitely looking at the geopolymers and understanding how these new solutions for solidifying or immobilizing solid wastes is suitable for the disposability. Then the last work package, in work package 7, I think ties in great to our next speaker as well. There are a lot of countries who do not have a repository yet, and we have packages waiting in interim storage and waiting and waiting and waiting, and we might have legacy wastes, which we don't know what there is. We might see some defects. We might worry about cracks or ASR. And so this work package is really looking at trying to understand what is in a package, in a concreted box, using non-destructive methodology, characterizing the packages, understanding do we need to do retreatment or reprocessing in that disposal phase. Also trying to help the owners who have a repository look at what digital twins or data simulations might be of an interim storage to make decisions and have risks early flagged, for instance, with artificial intelligence to say something's going wrong, which is better than what the human eye can see by looking at individual data Excels. So it's really a lot about the digitalization aspects for better optimization of how we handle the pre-disposal package integrity and understanding the durability of concrete. So what does all this mean to this community and to the vision of IGD-TP to get towards disposability? I hope this presentation has given you some food for thought to think it's not just all solved. There's still ways that we can optimize what we do in the early phases, which is going to help our whole community have lower amount of wastes in our repositories by applying this waste hierarchy, to have better understanding of waste acceptance criteria so that we can understand how to share facilities or how to have consistency when we communicate with our stakeholders to get ready for the disposability when the facilities are ready. We try to, in this project, really encourage to look holistically. It's not just about the technology, but it also has to be economic and it has to be sustainable. It has to show that the environmental footprint is not getting worse in the solutions that we create. So it needs to be all the way from upstream, from the ones who generate and own the waste, all the way through the disposal, and you who need to put it in the ground safely for millions of years. And we feel like we're the middle bridge between those two. And we hope that this project brings more of these digitalization aspects also from other sectors into the waste management and the repository and the pre-disposal aspects. And we hope, of course, that we get the next generation and our own middle-aged generation continuing in this field with the competences and the desire to stay in this field for human capacity. And altogether that we can continue to improve the technologies for these routes of waste handling and storage. So with that, I think we're at the halfway point. We've got a lot of results so far. We've got even more coming. If you are interested in this project, please see myself or any of our colleagues who are here. And we look forward to also really communicating and cooperating with the community to go forward for the next 5 to 10 years as well with this holistic approach. So with that, thank you.
Good morning, everybody. Thank you for the opportunity to give a talk here today. First of all, I have to say I am not from the radioactive waste community. I'm from the computational mechanics community. So I want to explain a bit how I came here. Yeah? So in 2019 to 2021, there was a roadmap initiated at the TU Braunschweig by Manfred Kraftschik, my colleague, head of the Institute of Computational Modeling and Civil Engineering, and Joachim Stahlmann, who has been working on geomechanical and geotechnics for the past years. He's a professor also at TU Braunschweig. And they initiated together the roadmap on artificial intelligence in radioactive waste disposal. Unfortunately, this roadmap is written in German, but yeah, anyways. So since in May 2021, I got appointed as assistant professor for data-driven modeling and simulation of mechanical systems. So at that time, we then had the roadmap. So we want to do something related to AI and radioactive waste disposal. And we had a new guy, that was me, who had the methods to tackle this problem. So we then wrote a proposal related to this roadmap, which is still under review. It's in the second phase now. So it's rather a question of when and not of if. But this to be said, I don't have any results to present, but rather some ideas how computational modeling, how artificial intelligence could serve the radioactive waste disposal community. I have 3 sections in my talk. The first is on digital twinning of radioactive waste repositories. So this motivates sort of our proposal. Then we have 2 different techniques, surrogate modeling for calibration and optimization. And I will also share some ideas on the statistical finite element method, which can be useful in monitoring and which can really relate numerical simulations and monitoring data. I had a buzzword in my title. This is the digital twin. Everybody wants to have it. Everybody wants to work on it, but we usually don't have a common interpretation. So I need to give my interpretation. So we look at the product lifecycle, which starts with the design and planning phase. This is where most of the projects here are at the moment. Then we have the production and construction. We have the operation, and we have the inspection and maintenance. What has been developed in the past are numerical models that are mostly based in the design and planning phase. But actually, over the entire product lifecycle, we have experiments, simulation, and also metrology, thus monitoring data. And the idea is now to merge all this information in order to yield a fully digital representation of a physical asset. So to have a digital representation of the reality. So this is our team where we applied for the proposal it's Joachim Stahlmann on the left, who is an expert on geomechanics and geotechnics. He has a long-term record in radioactive waste disposal. He's experienced in material modeling and also monitoring. And he provides us the physics-based model. So the question is now how we can make this physics-based model useful in practice. As I said, standard numerical tools are mostly situated in the design phase. So now we want to leverage also for the construction phase. I did my PhD in mechanics and then came for this assistant professorship on data-driven modeling and simulation. There's a joint, the link to Ulrich Römer comes via the surrogate modeling. Ulrich Römer is assistant professor for uncertainty quantification. I know there are no uncertainties in radioactive waste disposal, so we had this discussion during the proposal time. And we want to provide the data linkage to the physics-based model to make it useful in practice. And here was our prototype. It's a model of a storage drift with backfill and sealing plug. So we have the topology. We obtain a discretization of it. So we have a parametric virtual demonstrator, finite element simulation, finite difference simulation. And in this model, we have variable parameters. These are, first of all, material parameters that require calibration. And we have shape parameters that can be optimized for an optimal layout of the repository. So now let's have a look at the design loop, how we could use such a model in practice. We have a planning phase 1. We calibrate our model parameters based on laboratory experiments. That means on the site, we could drill a hole, we could drill another hole, we make some probes, and then we get some material parameters that are possibly wrong because or incomplete because of the testing conditions. But anyways, using the model that we have, it's the best that we can do. We will optimize the storage drift with backfill and sealing plug, and then we start to excavate. And no surprise, our as-planned model will deteriorate from the as-is model. That means when we look back at our product life cycle, we have a mismatch between the model in the as-planned phase and in the production and construction phase. And this mismatch we need to capture in order to update our digital twin. This is the idea. So what can we do? We can do a second calibration phase of the model parameters based on monitoring data. So we could measure the actual drift of the storage, and then we can do another optimization loop and then optimize our layout according to the actual conditions. So I know it's an applied community, and you need to build this in practice. So the question is, why do we need to do the math? Why so complicated? Why is it worth it? The point is that sensors can only display a fraction of an entire system. Yeah. So via monitoring, via sensors, we can access displacements, we can access strains, we can access temperature, but there's much of the reality which is hidden to us, and much which is really important, like the mechanical stresses. I could have a displacement field which I measure, and behind the displacement field there could be a stress field which says, okay, everything is fine, continue as you want. Or it could say, be careful, in a second you will have fracture. So in this we can decode using numerical tools. So here's an example of a wind turbine. In a wind turbine, for example, we could have displacement sensors, discrete sensors. And the idea would then be to relate these discrete measurements to a full field stress field, in order to have the full information and to see really where we could run into problems. So the inference of hidden quantities can improve our prognosis. It can help us with extrapolation of our material behavior in time, and avoids the look then into the crystal glass, and it can support expert in decision making. Yeah? So it will not replace an expert, it will just give further information to the expert. Now we'll talk a bit more about the methods on a conceptual, from a conceptual point of view. First of all, I want to focus on surrogate modeling for calibration and optimization. So what we said, we have a model, we need to adapt it. We need to adapt it to laboratory experiments. We need to adapt it to monitoring data. Yeah. In order to do so, we have input parameters on the left. These are our model parameters. For these model parameters, we evaluate our virtual demonstrator, our numerical model, and then we obtain an output quantity of interest. Yeah. So in our case, it would be we have the material parameters of the work model, and then we feed it into the numerical model, and then we get the storage drift. That would be our quantities of interest. So when we fit our model to actual measurements, then we need many calls of our numerical model because it's an iterative procedure. Yeah? So it's not a trial and error procedure, it's an optimization algorithm, but still it requires expensive numerical simulations. Now the idea is to use a surrogate model or a meta model that can learn the functional relationship. Output is then equal to a surrogate of the input. So this can be a regression ansatz. And then we do machine learning of the surrogate based on input-output data pairs. And this only requires a high computational one-time invest. So we can, once it's trained, we can use it again. And here we want to focus on Gaussian processes because they enable efficient training using adaptive sampling of design points. So here another graphical illustration. So the reality for us is represented by monitoring data. Of course, there's also some noise. I will come to that later. And here we measure the storage drift. And then we will observe a discrepancy between the measured and the simulated drift. The simulated drift is a function of the parameters, and that parameters is what we need to identify. Then we formulate an objective function, and this objective function is then iteratively optimized, or the parameters are iteratively optimized in order to minimize that objective function. So calibration means that we minimize our objective function to fit the model parameter to the measurement data. And since we need to evaluate the numerical model frequently for that, we can replace it by the surrogate model in order to reduce the computational cost within the calibration loop. And the same is true then also for the optimization loop. Here's the concept. We have two different surrogates. In the planning phase, we needed to calibrate, or in the planning phase, we needed to optimize our layout of the virtual demonstrator. Then we see that our virtual demonstrator deviates from the as-is model, and we use another surrogate for calibration after the excavation phase, and then we would have another optimization phase. So ideally, the virtual demonstrator and the monitoring data reflect as a digital twin the reality and support constructive decisions. This is the basic idea. So now, one problem is, or one shortcoming here is, for the calibration, once we have identified the real parameters that best represent our model, then it's still expensive to evaluate it. Yeah? So for monitoring, this will be expensive. Here we motivated it for the planning, it's fine. But then for monitoring, other approaches could be more interesting because we want to avoid solving a numerical model when we have a running sensing system. It has to be really fast then. So, and this brings me then to the statistical finite element method that we recently started working on, and back to this image of the wind turbine where we have displacement sensors, and from this displacement sensors we want to reconstruct the stress field. So basically, in engineering, we mostly have deterministic mathematical models that are often discretized and solved with finite elements. Of course, we can then also include uncertainties. These uncertainties then require frequent model evaluations. We could then do Monte Carlo simulations or polynomial chaos expansion in order to reduce the computational effort. But the question is how to link the measurement data to the stress distribution. And this is the idea here of the StatFem, statistical finite element method. We have the reality on the top left, but we cannot access the reality. Yeah? We only have an abstraction of the reality, that is the model, but the model is subject to an error. We have data, but also the data is not the reality. It's subject to noise. Yeah. So we need to reconstruct the reality based on all the inaccuracies, uncertainties that we have. Here's an example for different uncertainties. If we consider, for example, the displacement U here, our target quantity of interest, we have uncertainties in the material, we have uncertainties in our numerical discretization, in the shape, and also in the loading conditions. And this is something that we compute a priori. This is something that we compute in a design phase. And then the idea is to update these solutions based on the measurement data. Yeah? So we have then trainable parameters, that is the red circles, that is the scaling factor, that is the model error, which is represented by a Gaussian process. So we have then 3 trainable parameters that have to be fitted in order to update our solution. And this can be then really fast. So the idea is to compute, to use the numerical model in the design phase, have all this data generated with this model, and then use it to update our sensing information. This is based on Bayes' theorem. Bayes' theorem gives an expression for for posterior distribution. That means, given that we have observational data, what is the probability of our displacement U? So it's wrong here. Probability of U. It should be of our displacement. And in the Bayes' theorem, we then have trainable parameters. These the rho and the sigma d and the LD. So these model mismatch parameters. And from Bayes' theorem, we obtain another optimization problem that we solve to identify these parameters. And at the end, we can use these parameters then to update our solution. So this is the concept. On the left, we have observation data. It's discrete, not continuous. Yeah. In order to compute stresses, we would need a continuous ansatz that we don't have. But in the finite element simulation, we do have a continuous ansatz. We have these ansatz functions, so we can also compute stresses. But the finite element solution is not correct. So we update our finite element solution based on the statistical model, based on these hyperparameters that we determine in an optimization problem. And then we get what is shown here in the center. We get an updated solution, a continuous solution, a continuous ansatz. This we can feed back into our discretization scheme that we have. We compute the stresses, and this way we can get a continuous stress field based on sparse sensor data. This is the idea here. Okay, then I already want to come to a conclusion and summary. So I had 3 sections here in my talk. The first was digital twinning of radioactive waste repositories. We need to calibrate and our numerical models. We need to optimize parameters of our numerical model in order to make them useful in practice. It's not sufficient to only set the model up. We then also need to think of how can we use it. Yeah. Surrogate modeling can help us in reducing the computational effort and calibration and optimization. And methods like the statistical finite element method provide us opportunities to link data and simulation in order to infer quantities that we cannot measure, in order to provide experts additional information. Why that? I want to come back to the slides that I already showed. The thing is, sensors can only display a fraction of an entire system. We can measure displacements, strain, and temperature, but the interpretation of the sensing data is then either left to experts, or we help the expert in reconstructing stress field, heat flux, 3D fields of displacement, strain, and temperature in order to provide enhanced high-level information for the expert. And that way, a well-calibrated model can provide otherwise inaccessible information. It helps us to infer these hidden quantities and to improve prognosis and help to extrapolate the actual system behavior. Yeah, I think I'm quite early, but also my previous presenter was quite early. But maybe you have questions so we can fill the time. Thank you.